Number 41 from the book is another common ion type of problem. We have manganese hydroxide, which splits up into one manganese and two hydroxide ions. The KSP is going to be equal to the concentration of manganese times the concentration of hydroxide squared. And we are looking for the solubility, so we are given the KSP for manganese hydroxide. Rather, we look it up in the back of the book. But before we do that, all the concentrations are being talked about in terms of what's the pH. And I remind you, from first year chemistry, you learned that pH plus pOH always equals 14, and that the concentration of hydroxide is going to equal 10 raised to the negative pOH power. So we'll be seeing a lot of this type of conversion in our next unit, but right now it's easy enough to just show you that 14 minus the pH is going to equal pOH. So for my three conditions, A, B, and C, I can determine the pOH, like in A it's 7, and that the concentration of hydroxide, that's the common ion, is going to equal 10 to the negative 7th, or 1 times 10 to the negative 7. For B, my pOH turns out to be 4.5, and my concentration of hydroxide 3.2 times 10 to the negative 5. And for C, 2.2, and the concentration is 6.3 times 10 to the negative 3. What you can see here is that from A to B to C, the concentration of hydroxide is increasing. It's going up every time. So we can expect our solubility to go down because the amount of a common ion is larger in every single instance. So in the first one, in A, the pH is 7, and we already figured out that the concentration of hydroxide is going to be 1 times 10 to the minus 7. So, looking it up, you found that KSP is 1.6 times 10 to the minus 13. And this has to equal the concentration of the manganese ion times the concentration of the hydroxide ion squared, which is going to be 1 times 10 to the minus 7 squared. So for A, the concentration of the manganese ion is going to equal the KSP divided by the concentration of hydroxide squared. And that equals 16. Right. This is such a big concentration because normally the concentration in pure water has less hydroxide than this. So this here has the effect of letting more of it dissolve than it would in pure water. For B, it's the exact same approach, but now we have a different number for our concentration of hydroxide. This time it's 3.2 times 10 to the minus 5. So it's still going to be 1.6 times 10 to the minus 13. It's still going to be divided by the concentration of the hydroxide, but now 3.2 times 10 to the minus 5 squared. That's going to equal the concentration of the manganese ion. And this time it equals 1.6 times 10 to the minus 4. As expected, it dropped. Much less soluble with more of the common ion present. For part C, the concentration of hydroxide is 6.3 times 10 to the minus 3 squared. That's going to equal my concentration of manganese ion, which is going to equal the solubility, which is 3.6 times 10 to the minus 7. All right. In every one of these cases, because the hydroxide was being set for us as our common ion, the concentration of manganese is the molar solubility, because this is 1 for 1. So each of these molarities for the manganese ion is that there's 16 moles of manganese hydroxide that dissolves per liter. That these can all be moles per liter of manganese hydroxide that dissolve.